Why light knows where to go. You know, people have been asking, why does light behave the way it does for thousands of years? The ancient Greeks wondered about it. Islamic scholars in the Middle Ages puzzled over it. Then came fellows like Fermat, Huygens, Newton, and eventually Maxwell and Einstein. Each one added a piece to the puzzle. But here's the thing that bothered me. All these theories, even the good ones, described what light does without really explaining why it does it. Why does light reflect off a mirror at the same angle it comes in? Why does it bend when it goes from air into water? Why does it seem to know exactly which path to take? And the standard answer, that light takes the path that minimizes travel time, always felt incomplete to me. I mean, how does the light know which path is fastest? Does it scout out all the possibilities first? Does it have some kind of cosmic GPS? The answer, as I eventually figured out, is far more beautiful and strange than anyone imagined. Light doesn't choose anything. It takes every possible path, and I mean every path, and the path we see emerges from the way all these possibilities interfere with each other. Let me tell you how this works, because it's one of the most elegant things in all of physics. The mystery of reflection. Let's start simple. You shine a flashlight at a mirror. The light bounces off and hits your eye. Easy, right? Now, your high school physics teacher told you that the angle of incidence equals the angle of reflection. If the light comes in at 30 degrees from the perpendicular, it bounces off at 30 degrees on the other side. This is called the law of reflection, and it's been known since ancient times. But why? Why that particular angle? Why not some other angle? The traditional answer goes back to a French lawyer and mathematician named Pierre de Fermat in the 1600s. He said that light takes the path that requires the least time. For a mirror, the path that takes the least time happens to be the one where the angles are equal. You can prove this with a bit of calculus. It's actually quite elegant. But Fermat's principle always bothered me. It's teleological. It assumes light somehow knows where it's going and picks the fastest route. That's not how nature works. Nature doesn't plan ahead. It doesn't have goals. Things just happen according to local rules. So I thought there must be a better way to understand this. Every path contributes. Here's what actually happens, and I'm going to blow your mind a little bit. When light goes from the flashlight to the mirror to your eye, it doesn't just take the path your teacher drew on the blackboard. It takes every conceivable path. It takes the path that hits the mirror at the right spot, the one that makes equal angles. But it also takes paths that hit a little to the left of that spot, and paths that hit a little to the right, and paths that hit way over on the left edge of the mirror, and paths that hit way over on the right edge. Every single point on that mirror contributes to the light reaching your eye. Now you're thinking, Feynman, that's crazy. If light is coming from every point on the mirror, why do I see a sharp reflection? Why isn't everything just a blurry mess? That's where the magic happens. That's where quantum mechanics comes in. Little arrows spinning in the dark. Here's how we're going to think about this. For every path that light could take, we're going to draw a little arrow. This arrow represents what we call the probability amplitude for that path. Now, this arrow has a special property. It rotates. The amount it rotates depends on how much time it takes for light to travel that path. And here's the key. It rotates at a rate that depends on the frequency of the light. Let me be more specific. Imagine light traveling from point A, your flashlight, to point B, somewhere on the mirror, to point C, your eye. You calculate how long that takes, then you draw an arrow, and you rotate it by an amount proportional to that time. For blue light, which has a high frequency, the arrow spins really fast, many complete rotations for even a short time. For red light, which has a lower frequency, it spins more slowly. Now here's what you do. You draw one of these rotating arrows for every single path the light could take, and then you add them all up, tip to tail, like a chain of vectors. The final arrow you get, the sum of all these contributions, tells you the probability amplitude for light to get from your flashlight to your eye via that mirror. And the square of the length of that final arrow gives you the actual probability, or in this case, the intensity of the light you see, the miracle of interference. Now I'm going to show you why this explains the law of reflection without light having to know anything. Let's think about the path that hits the mirror at the spot where the angles are equal, the classical path. The one Fermat said takes the least time. Call this path 1. Now think about a path that hits the mirror just a tiny bit to the left of that spot. Call this path 2. How much longer does path 2 take compared to path 1? Here's the beautiful thing. If you're right at the point where the angles are equal, paths just to the left and just to the right take almost exactly the same time. The time is at a minimum there, or more precisely, at what mathematicians call an extremum. If you move just a tiny bit left or right from that optimal spot, the time barely changes. What does that mean for our spinning arrows? It means that path 1 and path 2, and path 3 that's a little bit to the right, and path 4 and path 5 all have arrows pointing in almost the same direction. They're nearly in phase with each other. When you add up arrows that are pointing in the same direction, they reinforce each other. You get a nice long final arrow. That means high probability amplitude. That means bright light, where the light isn't. But now look at paths that are far from the optimal spot. Consider a path that hits way over on the left side of the mirror, and another path that hits a bit to the right of that, and another a bit more to the right. These paths have very different travel times. One might take much longer than another. So their arrows point in wildly different directions. When you add them up, they tend to cancel out. One arrow points north, another points east, another points south. Add them all up and you get almost nothing. This is the heart of the whole thing. Paths near the classical path, the path of least time, contribute arrows that point in similar directions and add up constructively. Paths far from the classical path contribute arrows that point in random directions and cancel out. The light doesn't choose the shortest path. All paths contribute, but nature does the choosing for us automatically through the miracle of quantum interference, the width of the hot spot. Now you might ask, how wide is the region around the optimal point where paths contribute constructively? This is a great question, and the answer reveals something deep about the wave nature of light. The paths that contribute significantly are those within a region where the travel time doesn't differ by more than about one period of the light wave. For visible light, that's an incredibly short time, about 10 chiasm 15 seconds, or 1 femtosecond. But translated into distance on the mirror, this corresponds to a region that's roughly 1 wavelength across. For visible light, that's about half a micrometer, pretty small, but not infinitesimally small. This is why, in practice, the law of reflection works so well. The region contributing to the reflection is small enough that treating it as a single point, the classical picture, is an excellent approximation. But, and this is important, if you look carefully enough, you can see effects from those neighboring paths. This is why light diffracts around edges. This is why you get interference patterns. The quantum mechanical reality that all paths contribute manifests itself in these subtle effects. Let's talk about refraction. Now let's make things more interesting. What happens when light goes from air into water? You know from experience that a stick looks bent when you put it in water. That's because light bends when it enters the water. This is called refraction. The rule, discovered by Snell in the 1600s, says that the sine of the angle in air times the refractive index of air equals the sine of the angle in water times the refractive index of water. It's a simple rule, and it works perfectly. Fermat explained this by saying that light takes the path that minimizes time, and since light travels slower in water than in air, the quickest path is one that bends, spending less distance in the slower medium. But again, how does light know to do this? How does it know it's about to enter water? How does it calculate the optimal path? The answer, it doesn't. Once again, light takes every possible path. It goes straight across the boundary. It bends a lot to the left. It bends a lot to the right. It takes a curved path. It zigzags every path you can imagine. And once again, most of these paths cancel out because their arrows point in different directions. The only paths that survive, the ones with arrows pointing in similar directions, are those clustered around the path of least time, which happens to be the path that obeys Snell's law. The light doesn't know Snell's law. The light doesn't know anything. It's just that the fundamental quantum mechanical rules that all paths contribute, weighted by their action, automatically produces behavior that looks like the light is following Snell's law. The action, nature's accounting system. Let me get a bit more technical now, because there's something beautiful lurking here that connects to all of classical physics. I keep talking about time and how the arrow rotates based on how much time the path takes. But actually, what really matters is something called the action. For light, the action along a path is just the time it takes, multiplied by the frequency of the light, multiplied by Planck's constant. Well, technically, it's a bit more complicated, but this is the essence. The rule is the arrow rotates by an angle equal to the action divided by Planck's constant. Now, here's the thing. This concept of action is incredibly deep. It appears all over physics. In classical mechanics, there's a principle called the principle of least action that says particles follow the path that minimizes the action. This principle can be used to derive all of Newton's laws. What quantum mechanics does, and this is what I figured out, is generalize this. Instead of saying nature chooses the path of least action, we say nature explores all paths, and the contribution from each path depends on its action. When Planck's constant is very small compared to the typical action, which it is for everyday objects, only the path of least action survives the interference. This is why classical mechanics works. It's an approximation that emerges when quantum effects average out. But when Planck's constant is comparable to the action, as it is for microscopic systems like atoms and photons, the other paths matter. You get interference effects. You get quantum behavior. Why is light different from everything else? Now, I've been talking about light, but you might wonder, does this apply to everything? Do electrons take all possible paths? Do baseballs? The answer is yes. Everything follows these same rules. Electrons, protons, atoms, molecules, even baseballs in principle. But light is special in one way. It's easy to demonstrate these effects with light because light is easy to manipulate and detect. You can do the double-slit experiment with light using equipment from a hardware store. Also, for light traveling through empty space, the action is particularly simple. It's just the time multiplied by the frequency. For massive particles, there's an extra term from the kinetic energy, which makes the math a bit more complicated, but the principle is identical. The double-slit experiment revisited. Let me give you another example that really drives this home, the famous double-slit experiment. You have a light source, a barrier with two slits in it, and a screen on the far side. You shine light at the slits and look at the pattern on the screen. What do you see? Not two bright spots, which is what you'd expect if light just went through one slit or the other. Instead, you see alternating bright and dark bands, an interference pattern. The standard explanation is that light is a wave, and waves from the two slits interfere with each other. That's not wrong, but it's not the deepest explanation. Here's the path integral explanation. Light takes every possible path from the source to any point on the screen. Some of these paths go through the left slit, some go through the right slit, and, this is crucial, we have to add up the probability amplitudes from all these paths to get the final amplitude. Consider a point on the screen where you see a bright band. The paths through the left slit and the paths through the right slit arrive with their arrows pointing in roughly the same direction. They add up. You get a long final arrow, high amplitude, bright light. Now consider a point where you see a dark band. The paths through the left slit arrive with arrows pointing one way, and the paths through the right slit arrive with arrows pointing the opposite way. They cancel out. You get no final arrow, zero amplitude, no light. The interference pattern emerges naturally from adding up contributions from all possible paths. What if you block one slit? Here's where it gets really interesting. If you block one slit, the interference pattern disappears. You just see a broad, bright region corresponding to light spreading out from the open slit. Why? Because now there's only one set of paths contributing, the ones through the open slit. Without paths through the other slit, there's nothing for them to interfere with. This shows you that the interference isn't some mysterious interaction between particles. It's a fundamental consequence of adding up probability amplitudes from different paths. What if you try to detect which slit the light goes through? Now here's the really mind-bending part. What if you put a detector at each slit to see which slit each photon goes through? The moment you do this, the interference pattern disappears. Even though both slits are open, you see the same pattern as if you'd blocked one slit or the other. Why? Because detecting which slit the photon went through fundamentally changes the experiment. The detector interacts with the photon. And now you have to include all the paths involving that interaction in your sum. When you trace through the math, you find that paths through the left slit only contribute when the left detector clicks, and paths through the right slit only contribute when the right detector clicks. The paths can no longer interfere because they correspond to distinguishable final states. Detector 1 clicked versus detector 2 clicked. This isn't because the measurement disturbs the photon in some crude mechanical sense. It's because measurement is a physical interaction that must be included in the quantum mechanical description, and that interaction destroys the conditions necessary for interference. Light doesn't know anything. So here's what I want you to take away from all this. Light doesn't know where to go. It doesn't choose. It doesn't think. It doesn't plan. Light, like everything else in the universe, follows the fundamental quantum mechanical rule. Explore all possibilities, weight each one by its action, and let interference do the rest. The behavior we see, light reflecting, refracting, diffracting, interfering, emerges from this simple rule. The classical laws of optics, the laws that say light takes the shortest time or the least action, are approximations that work when quantum effects average out. But they're not the deepest truth. The deepest truth is that nature computes every possibility, and what we see is the result of a vast quantum mechanical calculation involving constructive and destructive interference of probability amplitudes. Quantum electrodynamics, the full story. Now, what I've been telling you so far is actually a simplified version. The real complete theory, the one that earned me a share of the Nobel Prize, is called quantum electrodynamics, or QED for short. In QED, we don't just consider different paths through space. We also consider all the different ways that photons can be emitted, absorbed, scattered, created, and destroyed. We consider all the different ways that electrons and other charged particles can interact with these photons. For instance, when you think about light traveling from point A to point B, it doesn't just go directly. It could emit a photon and reabsorb it. It could create an electron-positron pair that then annihilates. It could scatter off virtual particles in the vacuum. Every single one of these possibilities contributes to the final amplitude. And once again, most of them cancel out, but some don't. And the surviving contributions give us predictions that agree with experiment to absurd precision, something like 10 decimal places. This is the most accurately tested theory in all of physics, and it's built on this simple idea: add up all the possibilities, weight them by their action, and see what survives the interference. Feynman diagrams, pictures of possibilities. To keep track of all these possibilities, I invented a system of diagrams, what people now call Feynman diagrams. Each diagram represents a different way that particles can interact. For example, an electron emits a photon. Simple diagram: a line for the electron before, a line for the electron after, and a wavy line for the photon connecting them. Or an electron and a positron annihilate to create a photon, which then creates another electron-positron pair. Another diagram. Each diagram corresponds to a mathematical expression, a contribution to the probability amplitude. To calculate the probability for any process, you draw all the possible diagrams up to some level of complexity, calculate the contribution from each, and add them all up. These diagrams aren't just bookkeeping devices. They're pictures of all the different ways reality can happen. And just like with paths through space, most of them cancel out. But the sum of what remains matches what we observe with extraordinary precision. Why does this work? You might be wondering, why does nature work this way? Why this rule that you add up amplitudes from all possibilities? I don't know. Nobody knows. It's just how the universe seems to be built at its most fundamental level. I can tell you that this structure is deeply connected to the symmetries of nature, to things like conservation of energy and momentum, to the fact that the laws of physics are the same everywhere and at all times. There's a beautiful mathematical framework called gauge theory that shows how QED emerges almost inevitably from requiring certain symmetries. But even that doesn't answer the question of why the universe has those symmetries in the first place. At some point, you hit bedrock. You find rules that are so fundamental you can't explain them in terms of anything simpler. You can only say, this is how nature is, and isn't it beautiful? The Zen of light. There's something almost meditative about this picture of reality. Light doesn't strain to find the right path. It doesn't labor to solve optimization problems. It simply explores every possibility, and the universe does the accounting. The light that's hitting your eye right now, bouncing off this page, it got here by trying every route. Most of those routes canceled out. The constructive interference of the surviving paths is what you see. In a sense, the path that light appears to take, the one we calculate using classical optics, is just the most obvious symptom of all the quantum mechanical paths conspiring together. What this tells us about reality. I think this is one of the deepest insights quantum mechanics gives us. The universe is not lazy and it's not efficient. It's exhaustive. Nature doesn't take shortcuts. She computes everything. Every possibility is considered. Every path is explored. Every interaction is accounted for. And yet, out of this overwhelming complexity, out of this infinite consideration of possibilities, emerges the clean, simple world we see around us. Light reflects at equal angles. Light bends according to Snell's law. Objects follow Newton's laws. The classical world, the world of definite paths and certain outcomes, is a statistical shadow of a quantum mechanical reality where everything that can happen does happen in some sense. Does light really take all those paths? People always want to ask me, but Feynman, does light really take all those paths? Or is that just a mathematical trick for calculating the answer? And my response is, what do you mean by really? If a mathematical description predicts every experiment we can do with perfect accuracy, then in what sense is it not real? The paths we include in our sum are necessary for the calculation. Leave any of them out, and you get the wrong answer. On the other hand, we never see a photon taking multiple paths. We only ever detect it at one place. So in that sense, maybe the other paths aren't real. I think the question assumes we know what real means, and I'm not sure we do. The math works. The predictions match experiment. That's all physics can tell you. The rest is philosophy, light and consciousness. Sometimes people ask me if consciousness plays a role in any of this. Does the fact that we observe light force it to choose a path? No. The rules I've described work the same whether anyone is watching or not. Light was reflecting off mirrors and refracting through water long before there were any conscious observers around. What does happen is that when you make a measurement, when you interact with a quantum system in a way that records information, you become entangled with that system. Your measurement device, your eyes, your brain They all become part of the quantum state. And once you're entangled with the system, you can only see outcomes consistent with the branch you're on. That's why you see light taking one path, even though the complete quantum description includes all paths. But this has nothing to do with consciousness per se. A rock could be the observer if it interacts with the system in the right way. The democracy of paths. Here's what I love most about this picture. There's a democracy to it. No path is privileged. The path that light actually takes, the classical path, is just the one around which all the nearby paths happen to add up constructively. Under different circumstances, a different path might be the classical one. And in the quantum realm, when Planck's constant isn't negligible, all the paths really do matter equally. You can't ignore any of them without getting the wrong answer. This democracy extends to everything in quantum mechanics. There's no hierarchy of which possibilities are real and which are just mathematical. They all contribute. They all matter. Reality is not a single thread, but a tapestry of interfering possibilities. And what we call what happens is just the pattern that emerges from that interference, the poetry of physics. When I was young, I read a lot of poetry, and I always thought there was something poetic about physics, about understanding how nature works. But I don't think people realize how poetic this idea really is, that light explores every possibility, that reality is this vast interference pattern of quantum mechanical amplitudes, that the world we see emerges from the dance of probability arrows adding up and canceling out. It's more beautiful than any mythology humanity has invented. We live in a universe that computes every possibility, that contains, in some sense, every path not taken, every outcome that didn't happen, but that contributes to what did. Light doesn't know where to go, but in not knowing, in trying everything, it participates in the most elegant computational process in nature. And that, to me, is far more wonderful than any story about light choosing or knowing its path could ever be. The practical magic. And here's the kicker. This isn't just philosophy. This understanding that you have to sum over all paths, that you have to include all the ways things can happen, this is how we design modern technology. Lasers, transistors, computer chips, MRI machines, GPS, satellites, they all rely on understanding how quantum interference works. Engineers use these principles every day to build the devices we take for granted. The path integral formulation, the idea of summing over possibilities, is built into the quantum software that helps design drugs, that simulates materials, that does all sorts of practical calculations. So when I tell you light takes all possible paths, I'm not just spinning a philosophical yarn. I'm describing the actual computational method that works, that makes accurate predictions, that underlies modern technology. Nature figured out this trick billions of years ago. We're just catching up. I'd set down the chalk now, dust off my hands, and look at you with that characteristic Feynman intensity. So that's why light knows where to go. It doesn't know anything. It does everything. And in doing everything, in exploring every possibility with democracy and abandon, it creates the orderly, beautiful world of classical optics that humans have been studying for millennia. The universe doesn't think. It doesn't plan, it calculates. And the calculation involves every possibility, weighted by action, interfering according to the rules of quantum mechanics. And somehow, from that vast quantum computation, emerges light, bouncing off mirrors, bending through water, painting rainbows across the sky. Isn't that wonderful? Isn't that worth celebrating? Now, if you'll excuse me, I need to go play my bongos and think about antiparticles for a while.